Alright, this is a continuation of the Activity 19 videos. I'm going to walk through this proof with you together. And what we're trying to do is we're trying to prove this right triangle altitude theorem. The way that you prove a theorem is the hypothesis of that theorem is the given statement. That's what you're given, and you need to prove the conclusion. So we are given an altitude is drawn to the hypotenuse of a right triangle. So in here, the diagram, we have segment AS, that is the altitude of the right triangle AEY, the right angle being angle EAY. So if that's the case, if that happens, then we need to prove that the two triangles formed, meaning the small one and the medium sized one, the two triangles formed are similar to the original large right triangle and also to each other. Another way of writing that or saying that is we need to prove that all three of these right triangles in the diagram are similar to one another. So let's get after it. What we're going to do is the only thing we can use are these angles. And so the three ways of proving triangles similar, you have side-side-side similarity, side-angle-side similarity, and angle-angle similarity. We can't use side-side-side because we don't know any of the side lengths. We can't use side-angle-side because, once again, we don't have any of the side lengths. So our only hope in proving that these three triangles are similar is using angle-angle. We know that we have some right angles here, and all right angles are congruent. And we also see that some of the triangles share angles, like, for instance, angle Y, that's being shared by two of the triangles, and angle E is also being shared by two of the triangles. So that's kind of our game plan. That's how we're going to go about this. Statement 1 is, as always, what you are given. So we have triangle YEA with right angle EAY and altitude segment AS. So that's our given statement. As in class, as I conveyed, we need to add in a step in between 1 and 2. I'm going to call it step 1.5. And what we're going to say is that segment AS is perpendicular to segment EY. And so what I'm saying is this segment here, AS, is perpendicular to segment EY. And what justifies that is, well, I know that AS is an altitude. So the reason would be definition of altitude. Because we are given that it's an altitude, so we need to say that those two segments are perpendicular. And now we can say that these two angles, ESA and ASY, are right angles because of definition of perpendicular segments. From there, these two angles are right angles, so therefore these two angles are congruent to each other and also congruent to angle EAY because all right angles are congruent. All right angles are congruent. And this angle, angle EAY, that came from our given statement. It said that right angle EAY. So in statement 2, we're stating that these guys are right angles, and we already knew that this one was a right angle. That's why we can say that all three of them are congruent, because they're all right angles. Angle Y is congruent to angle Y because of the reflexive property of congruence. And then using angle Y and then these right angles, that allows us to say that triangle, we'll call it, we're going to use the large one, triangle EAY, and triangle ASY are similar to each other because those two triangles have right angles and they both share angle Y. So they are similar because of angle-angle similarity theorem. From there, I know that angle E is congruent to itself because of the reflexive property of congruence. Now, using angle E and then the three right angles, now I can say that the small triangle here that's using angle E and the large triangle are congruent to each other. We've already called the large triangle EAY, so I'm going to do that again. And the small triangle is going to be called EAS. Make sure that you're matching up the correct vertices. You're matching corresponding parts. I just used these names. That's where I got the names of the triangles. Those are printed for me, so it's really easy to identify what are the corresponding parts. And once again, these triangles are similar because of angle-angle similarity theorem. Now that I have that the large is similar to the medium, and then the large is also similar to the small, then I know that those two, this medium and small, are similar to one another by the transitive property. So all of these triangles are similar to one another because of the transitive property of similarities. So there you have it. There's that proof. You're looking for congruent right angles, angles that these triangles share, and then using angle-angle similarity theorem and then transitive property. Pretty easy proof. On the next page, you've got your homework. We're going to go over a lot of these questions in class, but it boils down to you identifying the three similar triangles and then matching up corresponding parts. I highly suggest that you redraw those three triangles. For instance, in this diagram on item 7, the large right triangle, I'm going to redraw all of the right triangles but have them in the same orientation. So it's easier to identify my corresponding parts. So here's my large, medium, and small. In this diagram, the large triangle, this vertex is B, this is C, and this is A. For the medium, this is C, this is D, and this is B. For my small one, this is D, this is C, this is A. Now that I have these separated and in the same orientation, it's very easy to see what my short legs are, what my long legs are, and then what my hypotenuses are. And then you can just label these diagrams and then just set up your proportions. Very, very simple. Moving on to the second part, however, second part of our lesson. Our learning targets are to identify the relationship that exists when an altitude is drawn to the hypotenuse of the right triangle. That's what we're trying to figure out. It's the same situation. We have this original large right triangle, and we have the altitude drawn to the hypotenuse. It's that same situation. And so we need to identify those relationships with the segments and angles and triangles, and then also we're going to have to apply those relationships that exist, and so meaning apply those to help us solve for missing side lengths. Item 1 says that we need to identify which two similar triangles allow us to show that this proportion is true. If we look, X is the short leg of the small triangle, so these dimensions of this first ratio are coming from that small triangle. And then we have T and Z, those two are coming from the medium triangle. So my left ratio is coming from my small triangle, my right ratio is coming from the medium triangle. My numerators, X and T, those are the short legs of those two triangles, and then T and Z, these two guys horizontally, these are the long legs of those two triangles. So it's just identifying these two similar triangles and then setting up a proportion by setting up corresponding parts. So which two triangles allow us to show this? This would be the small triangle and medium triangle. If we wanted to name these, which we need to, that would be triangle ESA, that's the small one, and then naming the medium one appropriately would be ASY. So these are my two similar triangles that allow me to write this proportion. The next one, we've got X, U, and then U and P. These first two lengths, or these dimensions, are coming from the small triangle once again. However, U and P are coming from the large triangle. All you need to do is just look, where is X and U? And they're right here. Those are two pieces of the small triangle. Where is U and P? U is this segment, and then P is that whole segment. That's two sides of the large triangle. That's how I'm identifying these triangles. Now let's see which parts of these two triangles. The numerators, X and U, those are the short legs of those two triangles, and then U and P are the hypotenuses of these two triangles. So we are just setting up a proportion using similar triangles and corresponding parts. This is exactly what we've done in the past when we first studied similar triangles, so we have learned nothing new. What the textbook wants us to do is to take these proportions and learn two corollaries. Corollaries, once again, are true statements that follow or that come from a theorem. And so what we're going to do is we're going to take this first proportion. In this first proportion, x over t and t over z. If we take this proportion and do the cross product, we're going to get t times t is equal to x times z. T times t is t squared and is equal to, and then the product of x and z. If I wanted to solve for z, if I wanted to solve for t, then what I could do is take the square root of both sides. The square root of t squared is just t, and the square root of the products x and z is just simply that. Well, this is the geometric mean. So if we look, we see that t is the square root of the product of these two numbers. That's the geometric mean.